All right, let's just jump right in. I have a question for you. Have you ever really, truly thought about the difference in brightness between a super sunny day and a clear, starry night? I mean, obviously one's bright and one's dark, we get that. But what if I told you the actual measurable difference is so huge, it's almost beyond our ability to even imagine? The difference is 100 million times. Yeah, let that number just sit there for a second. Not 1,000, not even 1,000,000. 100 million. And if that sounds completely insane, it's because our day-to-day experience gives us absolutely no context for a number that big. So that leads us to the big mystery here. If the world really gets 100 million times brighter when the sun rises, why don't we feel it? Why aren't we just completely blown out by the brightness of day and then totally blind at night? The answer is, well, it's fascinating, and it all starts with a little trick our own senses are playing on us. You see, the first piece of this puzzle isn't out there in the world. It's right here in our own eyes. Because as amazing as our eyes are, they are not objective measuring tools. In fact, they can be pretty deceptive. And this statement gets right to the heart of it. Our eyes are just not designed to accurately judge brightness. We can tell if something is brighter or dimmer than something else, sure, but we have no real sense of the scale. Is that light twice as bright? 10 times brighter? 100? Our eyes just kind of shrug and say, it's brighter. The source material gives a perfect example of this. Imagine the light shining on your keyboard is, say, 200 units of brightness, and the light on your desk, maybe just a few inches away, is 100 units. Objectively, the brightness was just cut in half. But does it feel half as bright? No way, not even close. So to really get what's going on, we have to move beyond what our senses tell us. So if we can't trust our eyes to give us the real story, what can we trust? Well, science, of course. To make any sense of this, we need an objective, scientific way to measure it all. And the key term we need to know is illuminance. It's just the official scientific way of talking about how much light is actually falling on a certain area. And its unit of measurement is the lux, which we write as LX. So from here on out, when we talk about brightness, we're really talking about illuminance, measured in lux. And this is how we do it. This little gadget is an exposure meter, sometimes called a luximeter. Professional photographers live and die by these things because they know for a fact their eyes will lie to them. This tool doesn't lie. It gives us the cold, hard numbers our senses just can't. It lets us see the world of light as it actually is. Okay, now that we have our tool, the lux, let's take a quick tour of our world and see what these numbers actually look like in practice. We're going to build the case for that 100 million times difference. And we're going to start at the very, very bottom. Our journey starts under a beautiful, clear, moonless night sky, far away from any city lights. The illuminance here is an almost unbelievably small 0.001 lux. That's our baseline. This is pretty much the darkest natural environment we can experience. Now watch this. Let's add a full moon to that same night sky. The brightness doesn't just go up a little, it jumps all the way to about 1 lux. Now think about that. We went from 1,000th of a lux to 1 whole lux. That's a 1,000 times increase in brightness just from the light of the moon. Okay, let's step inside now. A normal, comfortably lit room measures around 300 lux. We just made another huge jump, right? From 1 lux under the moonlight to 300 lux in a room. It's a massive difference on paper, but to us, it just feels normal. And finally, the top of the scale. Let's step outside into a bright, sunny day. The illuminance absolutely skyrockets to a staggering 100,000 lux. That's more than 300 times brighter than your indoor lights. Yet we walk outside every day and our eyes just deal with it. It's incredible. So let's put this all together. This table lays out the whole spectrum for us. You've got 100,000 lux at the top for a sunny day. Then look at the drop to a cloudy day. Then a department store, our room, a street light, all the way down to a single lux for moonlight. And finally, that tiny 0.001 for a starry sky. Seeing all the numbers laid out like this really hammers home the unbelievable range we live in every single day. So we've seen the evidence. We have the numbers, from the darkest darks to the brightest brights. Now it's time to bring this all home and prove that mind-blowing claim from the very beginning. Here we go. Here are our two extremes, side by side. The brightest we normally experience, 100,000 lux, and the dimmest, 0.001 lux. The final question is simple, really. How many times does that tiny number go into that massive one? And when you do the math, 100,000 divided by 0.001, the answer is, you guessed it, exactly 100 million. So the claim at the start, it wasn't just clickbait, it's a measured scientific fact. Thanks to our understanding of lux, we know for certain the difference is truly that immense. And this brings us full circle, right back to our original mystery. The reason we don't feel this 100 million times difference is because that's the true magic of the human eye. It wasn't built to be a precise meter. It was built to adapt. Your iris physically changes size, different cells in your retina take over. It's this incredible biological machine that allows us to see across that entire astonishing range. It really makes you wonder, doesn't it? And this is just our perception of brightness. What other incredible feats of filtering, of processing, of adapting are our senses doing every single second, completely behind the scenes? The world we think we see might not be the world that's actually there.